There's quite a lot to unpack here, but in the interest of time, I'll give you a high-level overview. So there are very many important data resources that have been created and maintained over the last few decades, like MinDat, EarthChem, RUF, and many more. In order for the data to be used to its fullest potential, we need to first process, represent, and analyze the data in a meaningful way. This can be either visual, like the network that you see on the screen now, or algorithmic, like the association rules you see on the screen, which are based on mineral occurrences. As a side note, I just want to also mention that this network that you're seeing is a very recent network that I created less than like a month or two ago, with all 5,700 minerals and all 57 paragenetic modes. And this, to our knowledge, is the first visual representation of all of mineralogy in one way. Anyways, getting back to the ecosystem part of it, we extract the information presented to us from the data, right? The next step would be to gain scientific insights or knowledge from this information. For example, if you had association rules generated by a certain algorithm, we can take those association rules and use them to predict where to find a certain mineral on Earth, like Tephroite, or where to find certain mineral assemblages on Earth or even Mars. So when I usually present this theory, this data information ecosystem to others, the most frequently asked question I get is, what role does my scientific domain play in this ecosystem? So the answer to that is it's everywhere. It's in every step. The transitions from data to information to knowledge and back are all within the confines of a given scientific domain based on the context of the situation. An important thing I'd like to mention here is that while a lot of examples that you're going to see today are going to be using mineral data, some using fossil data, I'd like all of you to think about this in terms of your own data, these methods and how they can be applied to your own data, because the methods that I'm working with and creating or helping create can be applied to minerals, to fossils, to microbes, to gas molecules, to very many different types of data sets. So research and collaboration in data science is a little different from what I've observed in other fields or domains. Data scientists usually have a background in fundamental computer science or mathematics on some level, and apply the algorithms they've either created or studied on data from various domains. This is usually done in collaboration with a domain scientist who's interested in answering a particular scientific question that's central to their research, or to explore the data to find trends that may generate new hypotheses. We usually start this by having a datathon. So you can see us having a datathon on the image on your screen. But the point I'm trying to make here is that data science research is very much a collaborative socio-technical system. In these collaborations, my role as a data scientist is to help answer scientific questions based on what I can learn from the data. Also, it's through attempting to answer these scientific questions using data-driven methods that I often find gaps in data science. This presents me with a great opportunity to then delve into the algorithms, the data structure, the math behind them, to conduct novel data science and computer science research, which in turn leads to publications and advances in that field. So this is going to be a repeating theme, but I'll say it once more. The relationship between the data scientist and, say, earth and planetary scientists or paleontologists is very much a symbiotic one. In short, here's what I do. Well, at least some of what I do. My expertise spans the entire spectrum of the data lifecycle. So it goes from creating, compiling, and integrating data resources to publishing data and making recommendations about curation and maintenance of data resources, and most importantly, on how to utilize data to gain important scientific insights. While the first 3 points that I mentioned in the slide are extremely important and essential to be able to get to the following analytics, my main interest and most of my work focuses on the last 3 steps, focuses on using data-driven methods to gain important knowledge from the data. This is also what I'll be mainly highlighting in this presentation. This part of the life cycle involves creating visualizations for complex data, analyzing the data using descriptive, predictive, or prescriptive methods, and finally gaining scientific insights using these methods. This is my main interest because, in my opinion, this is the most direct path to scientific discoveries. So with that sort of prologue out of the way, let's discuss with many examples how to leverage data science to push the boundaries of your domain and how that helps us data scientists too. Most data science collaborations start when researchers approach us with their data. Usually goes one of two ways. First, either the researcher has a research question in mind and they don't know how best to use their data to answer that question. Or second, researchers have had access to data that they've either collected themselves or just have had access to it over the years and just want to explore it. Both of these scenarios work very well because anyways, we need to explore the data as an initial step. So either you come to us with some data and we generally explore the data, or you come with a research question and then we explore the data, but in a more curated manner with the aim of answering your research question. The first example of such an exploration that has led to some scientific discoveries is that of association analysis. The idea and the resulting project started a few years ago when we were discussing the big questions of mineralogy that still remained unanswered. And I realized that one of the simplest but most important questions in mineralogy was where to go and find minerals. This got me thinking about mineral occurrences and how we can use the patterns in known occurrences of minerals to predict where to other similarly unknown minerals. So the idea I came up with then is what led to the mineral association analysis we've done, work that we've done so far, and we have a lot more future work planned. The association analysis method acts kind of like a recommender system where it looks at mineral occurrences the same way Amazon looks at what you purchased or Netflix looks at what movies you watched and tries to recommend to you or predict to you what movies you'd like to watch next or what things you might want to buy off of Amazon or something like that. Association analysis then, when applied to minerals, looks at mineral localities in the same way and mineral occurrences in the same way. It looks at mineral occurrences in all localities and forms association rules based on the frequency of occurrences of certain mineral assemblages. For example, if calcite and pumpelite occur, then it's highly likely that quartz is occurring at that same locality. There are some metrics that help us rank some of these rules that are formed. This will primarily be based on the frequency of occurrence of a certain mineral assemblage and the likelihood of that same mineral assemblage occurring in other localities. So I have some sort of visual representations or summaries of some of the rules in our rule base. So a graphical representation of 51 such rules from our rule base shows us that quartz is very essential to most of our rules and plays a central role. Another visual representation of the rules in our rule base is this matrix view, which shows us, for example, when albite and hydroxyl herderite occur together, then it's highly likely that bertrandite will be found at that locality as well. So what we do is we have these many rules that were generated by our algorithm to form a rule base, and we take these rules in a rule base and then query them against our data to make our final predictions. So when we do this, a prediction looks like what you see on the screen now. We are saying that you're likely to find tephroite at 4 localities on Earth. A couple of them are in Kazakhstan. One of those localities is in the US, in Virginia, and another locality in Sweden. So we're basically making a prediction for mineral researchers or enthusiasts to go find different types of minerals in the world. One thing I'd like to highlight here is that it's rare that an existing algorithm perfectly fits a given research application. There's usually quite a bit of modification, adaptation, or improvement required, whether this be on the algorithmic side or on the problem formulation side. For example, association analysis as a method was created back in 1994. It was primarily created for analyzing sales and purchase patterns, things that you buy from Walmart and so on. Most of the research that followed as a result was how to deal with different types of data or larger data sets in the same field. So in the sales example, we see that a small set of items are sold totally, right? Like there's like a fixed set of items that are being bought, but there are a lot of customer transactions, a lot of customers buying those items in various combinations. So the data kind of looks like this. You have like 20 odd columns, you have say 10,000 rows. So even if you were to scale this up, and the number of rows goes up from 10,000 to 100,000, there still isn't too much change in the number of columns. You might go from 20 to 50. But in case of minerals, that's very different. You end up with a whole new type of data problem, big data problem. So you have at least 2,000 plus columns, right? You have 2,000 plus minerals that are occurring in 100,000 localities. And this is the data that we've been able to run so far. This is how much we've been able to scale up. But in an ideal case, I want to run it on all minerals in all localities on Earth at least, and that would be 5,000 plus minerals. There's 5,700 minerals, known mineral species there, and MINDAT and the Mineral Evolution Database have up to 500,000 known localities. So scaling up is ongoing and requires algorithmic innovation. In addition to that, what I'd like to do also with this project, with this sort of research, is to increase the dimensionality of the association rules that are produced by this algorithm. I understand that I haven't explained the sort of technical details, but what this step will help us do is to predict the occurrence of a more complex mineral assemblage. So far we've been able to predict the mineral assemblages up to size 4, but I'd like to go to at least 15 minerals in a mineral assemblage, and also include rarer occurring minerals in our algorithm as well, which we've not been able to do so far. So this work will further, as I mentioned, both the fields of data science and earth and planetary sciences. Data science is advanced by adapting association rule mining techniques to solve the data dimensionality problem, to handle the new kind of big data problem. Another thing that I haven't mentioned, which we are doing, which is ongoing work, is we've created an evaluation method to better evaluate the resilience of the rules generated, thereby to better evaluate our predictions, to make better predictions in the future. On the earth and planetary science side, this will allow us to predict previously unknown mineral occurrences, including mineral assemblages, whether it's on Earth or on other planets like Mars. Using this technique, we also plan to predict analog environments. So I envision quite a few papers being written about this work, highlighting the contributions to both fields. I've written some of the papers that we've planned are in development here. And so all of the work that's being done right now is, I just highlighted them in blue, and the stuff in white is part of our future work, which is probably in the near future, not too much in the long term. We're going to get to it very soon. Another interesting aspect I wanted to mention in terms of association analysis is a project we have planned in collaboration with Donato Giovanelli, where we plan to explore association-based occurrences. So this is very nascent. We haven't started work on this, but we planned this and we'll start again soon. So after association analysis, another interesting opportunity I wanted to present today and discuss today is that of a small data framework. The idea here, much like the association analysis, goes back, I think, about 4 years ago now, when I was working on data from the ChemMin instrument on board the Mars Science Laboratory. I noticed that there were very few data points. Each mineral group had at most 200 rows. And we wanted to see if we could predict the chemical composition of the minerals simply based on the unit cell parameters. So while this was my first time working with such a small amount of data at the time, as I did more work, it quickly became clear to me that this is a fairly common occurrence in planetary sciences and a few other domains. For example, when you look at mineral data sets on Earth, the dimensions look something like this, right? Like you have manganese data sets and you have like a few thousand rows, you have 20 or so 30 columns or something like that, with each column being a parameter. But when you do the same thing, when you look at mineral data from Mars, these are the kind of dimensions you're dealing with: 86 rows by 13 columns. There's not a lot of data here in terms of the rows for you to be able to apply big data methods. So the trick is, like, most of the focus for most researchers in the world is big data, how to scale up machine learning methods to work with very large data sets. There's not a lot of work being done on, say, small data or sparse data or other kinds of complex data sets, which are a frequent occurrence that in my observation in Earth and planetary science research. So this is the idea behind the small data framework, but I'll get to that in a minute. But I'll continue with the ChemMin data set and what we did, right, that helped contribute to the small data framework. What we noticed when we were working with the ChemMin data set was that we used the label distribution learning paradigm, and we found that it worked very well in predicting multi-component mineral compositions, simply based on the unit cell parameters. So there's some papers in prep. Hopefully they'll get done soon, but this has been a pretty good success, and we'd like to keep exploring what else works with different kinds of small data sets. So this is just one example, like I told you in the interest of time. But if any of you have this kind of data and would like to work with me on it, please let me know. I'm very interested and looking for use cases for small data, for sparse data, for any kind of heterogeneous data, and so on. Anyway, the takeaway here is that answers to key scientific questions are often tied to small or other underutilized types of data. So an effort to create a framework or a roadmap to handle such data will be very beneficial to scientific research in all domains, many, many domains. I've listed some contributions in both, data science and earth and planetary sciences here. But even for this slide, I'd really like to populate it more with contributions from other domains and work with data from other domains that have similar, smaller, sparse problems. Same as before, the stuff that's ongoing is in blue, and white bullet points are stuff that we're going to get to in the future, but we very much plan to do. Again, I covered small data. This is the next sort of immediate thing. There's a few more types of data that I said that require our focus. One of them is, sparse data. The example here goes back to the work we did as part of the Deep Carbon Observatory's Census of Deep Life project, where we're working with microbial data. We have features, we have attributes like temperature, pH, conductivity, pressure, and other attributes from marine and terrestrial subsurface habitats. So if you look at this data, you'll notice one thing, is that there's a lot of missing values, right? There's a lot of missing data. So any exploration that we want to do into this data, any insights that we want to gain from here are very much hampered by the large amount of missing data. So any algorithms we use, any methods we use, need to overcome this particular hurdle and then go on to find hidden trends and patterns in the data. So I just wanted to make this point, like there's sparse data problems, and work needs to be done to fix that too, something that we're also doing. And the last part of this, different types of data for a framework, I'd like to talk about heterogeneous data. Heterogeneous data, again, is one of those things that has been an ever-present problem that has been underexplored. There's quite a lot of people working on solving this, but it's not solved because it's such a difficult problem. It's underexplored. These days, we get data from so many different sources. We either get data from scientific literature or books, so we parse them, extract them, rescue the data from there. There's experimentally generated data. There's observed data using telescopes or satellites, or even data that's been generated using various computer simulations. These data sets are usually incompatible with each other because they have various different data types, different data formats, data structures. Most of the time, what's done is that each of this data is processed on its own and analyzed on its own. And this kind of siloed approach means that there's a lot of chaos, right? And you can see that the chaotic figure that I've made, but it means that we can't really leverage data from other sources, let alone other domains, and integrate it together to really answer the big science questions that we want to answer. Like I said, there's been a good amount of research, but we're still constantly trying to improve the efficiency to work with truly heterogeneous data. So in an ideal world, or in my ideal world, this is what the figure looks like. This is what working with heterogeneous data looks like. We'd be able to seamlessly handle different types of data. We will even have data objects with multiple types in it. There's no such thing as metadata in an ideal world, because everything is data and everything is easily usable. So the impact of achieving, working with actually heterogeneous data really changes the way collaborative research is conducted. But it is a very difficult problem to solve. So we're constantly looking to chip away at the problems that occur with heterogeneous data, solving one problem after the other with the larger goal in mind. The last big topic I wanted to discuss today is that of network science. I know it's a topic that's probably familiar to a lot of researchers in this group, and you've seen others present or talk about this. But today I wanted to talk about this topic in the context of my research in improving the state of the art for the field of network science itself. And I'll be using examples from the work I've done in the past or that I'm doing currently to make that point. So the first topic or subtopic in network science that I wanted to discuss is network reduction. So we use network data as, if you've used it in the past, you use it to both analytically and visually represent the data and analyze it, right, to explore it. Because network science and network representations really help us view our data and gain scientific insights from a data in a way that commonly used analytics methods or analysis methods don't let us do. But as networks get larger and more complex, while we can still identify and analyze patterns in the entire network, it becomes increasingly difficult for us to explore specific parts of the network and notice some of the intricacies in the network or their subsets. For example, the network that you see on the screen is a fossil network that I created, I don't know how many years ago now, but it represents the animal family coexistence. So when I rendered this network for the first time, a few things jumped out at me simply based on the visuals alone. The first thing was the obvious time axis going from left to right, from the Cambrian fauna to the modern fauna. And the second were the pinch points, these pinch points. So when we were discussing and exploring these pinch points, we found that these pinch points represented mass extinction events. Long story short, this ended up being a novel method to identify punctuated events in fossil records. But even with these interesting findings, what if I asked you to give me insights about a particular subset, like this red group or this black subgroup with Paleozoic fauna or modern fauna, and tell me what patterns or intricacies you see there? That becomes a little difficult because of how dense this network is. So this is where network reduction comes in. How, if we were able to compress this network and its representation into something like this, now we can see not just the connections, but we can see properly subgroups that are formed and the connections between the subgroups. So let's explore this reduced network representation. Here we see the same three groups as before. We see the three big groups corresponding to, and the corresponding pinch points representing those mass extinction events. But when you look at the subgroups that I was talking about, smaller parts of the network, the first subgroup that we explored points to another very well-known extinction event around 66 million years ago, the one where the dinosaurs went extinct. And what happened when we explored the subgroup right next to it was that we found a previously unknown minor extinction event that occurred around 56 million years ago. This is what I mean. This shows the predictive power of such methods. An interesting side note about that, that sort of previously unknown extinction event. Recently, Morgan Schaller from RPI went into the rock records and was able to find 4 places in the east coast of the United States that have a record of this period in history, and found what may have caused this extinction event. In short answer, what he found was, there was a comet impact followed by widespread wildfires, global temperatures going up, and so on. But at the core of this discovery is this reduced network representation. And the initial rendering that I created for this network was done after manually discussing it with my collaborators, Drew Musenti and Andy Knoll. But it really got me thinking about the fact that there has to be an easier or a more generalized way to create a reduced network representation. When I looked into the literature, there weren't many viable ways to do this. So this is where my concept of network reduction comes in. Network reduction is a method by which we can compress both visually and mathematically the representation of a network. This is done for easier readability, for better analytics applications, and for finally, and more importantly, gaining scientific insights from our data. So I plan to create this representation. This is ongoing work, but what we're planning to do is create this reduced representation by using network partitioning algorithms and then creating subsets of these networks and creating network metrics that will aggregate the weights of all the nodes and edges in that subset based on the data parameters that are used. Thus, while there will be a reduced visual representation, there theoretically should be minimal loss of information. The second topic, continuing on with the network science research that I want to talk about, is multi-layered networks. So this method of multi-layered networks has been used in web science, epidemiology, and transportation. But from what I've seen, no one's fully leveraging this method in Earth and planetary sciences. This method is similar to the concept of network reduction. This research also deals with complex networks, but it actually takes it a step further. So let's say you want to study carbon minerals, and so you create a network of carbon minerals. First, you create a network of carbon minerals connected to its geologic localities, and then you also create a carbon mineral network of these minerals connected to their paragenetic modes, or based on their formational conditions. Usually, or most of the time, researchers these days, we all explore these mineral environments independently, right? But we know that these are interconnected, intimately related parameters that form a part of the whole carbon mineral system. So the important question here that we ask is, how can we compare these and more mineral parameters to study the overall relationships as one singular complex system? An answer to this question may be obtained using multi-layered networks. That's at least my view of this. So what you see on the screen now is a visual representation of multi-layered networks. We have multiple layers that have some commonality of nodes between them. And it also allows for connection between each layer and the nodes within the same layer as well. So if we apply my idea of studying mineral networks with these kind of methods, the common nodes in all of the layers could be mineral species. So layer 0 could be a network of minerals and their localities. Layer 1 could be a network of minerals and their paragenetic modes. Layer 2 could be minerals and their ages, and so on. Right? What we can do with this is study the combinatorial effect of these networks on a larger, complex mineral system. This helps us answer scientific questions that pertain to Earth's mineralogy as a whole interconnected and complex system, rather than the common way to study this, which is examine the effect of one or a few small number of parameters at once. With this method, we can see how dozens of parameters correlate in a system and how those mineral environments interact and evolve. There's been a good amount of research done in the area of multi-layered networks. So you can take commonly known network metrics and methods, and there's already research done on how to apply it to multi-layered network studies. Not only that, also you cannot just visualize these sort of layers in a multi-layered network in a linear manner. There's more complex representations of that too. So you can see on the bottom left in figure D here, there's a 2x2 layer matrix in an XYZ coordinate system. So there's even relationship between the layers themselves. And on the right in figure E, you see that the combined effect of such a complex layer system can also be visually represented in that figure. So this is a very interesting and evolving area that would be very beneficial to apply to not only mineral data, but other kinds of data. So the last idea that I want to discuss today is that of granular network metrics. So as you know, if you're familiar with using network analysis or network science, you know that network metrics are either local, meaning they're applied to one node or one edge at a time, or they're global, meaning they're applied to the entire network at a time. But what if we want to understand the behavior of a subgraph? So if you have to go and study a network right now, and I tell you, okay, you have this network of chromium minerals, and I want you to study this subgroup, this subgraph of that mineral network. The common way to do this is to apply a global network metric to simply this subgraph by discarding all of the other nodes. Obviously, researchers do this because there isn't an established way to analyze these subgraphs, and because there isn't a set of metrics that takes into account the relationship of the subgraph to the larger network. So my goal here is to do exactly that, is to create a set of network metrics that can be analyzed on a spectrum of network data. So this metric is granular, so you can define its granularity. You can either analyze it for just one node or any group of nodes or the entire network, while preserving the context and the relationship of the subnetwork to the larger network. So as usual, I see this work having wide-reaching impact. I'm very passionate about this work, and I think it'll be applicable not just to Earth and planetary sciences, but to many other domains, and also make fundamental advances in network science and data science itself. Specifically, the data science contributions include reduced mathematical representations with minimal uncertainty and loss of information, novel application of multi-layered methods to mineral systems. I see at least two papers coming out, these two papers coming out for now, including the granular metrics. But that's just what I'm envisioning now. As the research pans out, more papers might fall out. Additionally, in addition to both of these papers and these research venues, this kind of research also really makes advances in Earth and planetary science, evolutionary system of mineralogy paper series that is ongoing. And it'll really help us look at increasingly complex mineral systems that are being made there. And it'll also help us characterize the coevolution of geosphere and biosphere better for our planet and other planets as well. So I know I said last idea, but I guess I kind of lied. I really wanted to highlight this one project, which is very new and very interesting, that has developed over the last 2 months, which is being led by Mike Wong, a postdoctoral fellow at Carnegie. This exploration of ours, the reason I'm mentioning this is because all the advances made in multi-layered networks and granular metrics really will benefit this project as well. So this goes back to about 2 months ago, where we were discussing the results of chemical networks of a planet's atmosphere from a few papers, specifically a 2004 paper, which had these figures, or versions of these figures. So we're looking at this figure, exploring the assortativity of various planetary atmospheric networks. And we noticed that Earth's atmosphere is far more disassortative, has a different assortativity than all of the other planets. As a side note, assortativity is a measure of homogeneity of the nodes in a network, which means it's a node's tendency to connect to only similar nodes and not connect to dissimilar nodes. So again, Earth's chemical network is very disassortative compared to other planets. So we were having discussions on why this anomaly might occur, and it led us to make this sort of hypothesis or this research question that if the biology of a planet is what impacts the chemical network structure, because Earth is different from Venus and Titan and all that, then how do the different metabolisms that emerge in the planet also impact the chemical networks? So we created a set of networks, atmospheric networks, based on the chemical activities happening, the chemical compositions of the atmosphere. These are, again, very new figures, right? They're unpublished and everything, but so these figures, I think, are like a few weeks old, and we're exploring patterns. Still, we haven't found everything that needs to be found, but the initial findings are very promising. Especially, we've noticed patterns in the Earth's atmosphere as it evolves over time, and what human activity does to the Earth's atmosphere, how it was before human activity, before the Great Oxidation event, and so on. And lastly, the more ambitious goal for this project, for this idea, is to see if we can generalize network structures that we've observed to actually indicate potential biosignatures in planets. We plan to do this by analyzing chemical networks of a harbor world that has been simulated to evolve from an atmosphere with very different from Earth, and thus will have a differently evolved biology compared to ours. And then we'll compare the chemical networks of Earth to chemical networks of these harbor worlds to see if we can generalize a network structure to learn about potential biosignatures. So with this, we've reached the end of my presentation and what I wanted to highlight. I'd like to take this opportunity to highlight some of my collaborators who have been directly involved with the ideas I presented in the talk today. This work would not have been possible, let alone as fun, productive, and impactful without all of these people. I hope through this talk I've given some sort of insight, and I've been able to show you some of the ways we can push boundaries in our respective fields. And so let's make discoveries together. Lastly, I'd like to thank the organization and the organizations and funding agencies that supported the work that has been done and presented in this talk. Thank you.
Okay, thank you very much, Anirudh. So now it's time for questions from our participants. So if you have a question, feel free to open your mic or leave your question in the chat, and I could read the question on your behalf. Okay, I can start with the first one, a quick question that relevant to the Earth, Mars, Titan atmosphere figure. So, so for that, I just need some more clarification. So what are the input parameters? So are you listing all the different molecules in the atmosphere that you think that were possible, as well as their concentrations? And then what else?
Correct. So
what else information?
So there's, let me just pull up the figure. So yeah, so the components of the network are simply, you know, the geochemical composition of the atmospheres and how the different components of the atmosphere interact with each other. So if H2O in the atmosphere interacts with something else and there's a chemical reaction that happens to form a different compound, then those are the connections that are drawn. And to answer your question on whether it's all the possible geochemical components or not, we are doing 2 or 3 kinds of networks for Earth at least. One is from in an established textbook that has all of the components, the geochemical components of the network. So we're just using the data from that textbook. I'm trying to remember which one it was, but I think Mike Wong would know it better. The second one is using the simulation, one of the popular simulation methods that was run that takes into account all of the chlorofluorocarbons and other sort of, as activity evolves, more compounds are in the Earth's atmosphere, right? So there's 2 main data sources for creating these networks. One is from the textbook, which is sort of established. The second is through running a popular simulation method, which tells you a result of all of the geochemistry of the Earth's atmosphere. Does that help?
Okay, actually, then it turns out I have 2 following questions relevant to this.
Sure.
So do those reactions that consider this photon involved thing? Because in the current do those chemical reactions involve photon?
Photons?
Yeah. So it varies, because for modern Earth, we probably don't have to consider that. But if it look for some other planets without the magnetic field, we might consider. And also for the very early Earth, maybe the one that is shown earlier on, like Hadean Earth, we are not sure. There might be, like say, we have to consider adding or losing photons in these reactions. Then that will be very different systems that we're talking about. So I just don't know that in this system that whether this involving. And this also brings, this brings me a second question relevant to this is that if I from my visual understanding that modern Earth has much less network, so could that be related to that? Because I think in some other planets that
So there's two modern Earth networks. There's two modern Earth networks. One's far more dense than the other. This is the less dense one. Like I said, right? One's from the textbook and one's from the simulation. So one uses fairly lesser number of network nodes because it's only the ones that were considered important according to the textbook. The other one we use everything. So yes, there are two. So you're looking at the smaller one. For the first question that you asked, that's a very good question. Unfortunately, I don't know the answer. This is what I meant by most of these things I have to work in combination with the domain scientist. So the domain expert, who's Mike Wong, will know the answer to your question about the photons. So I'm kind of glad that this is being recorded so I can show him the question and maybe he can help answer it. So if you shoot me an email, then we can get that conversation going to help answer your question.
So my another naive question is that the less complex of the network, that means I could translate to less reactions or less entropy in terms of the reactions.
Sure, less reaction. Yeah.
Okay.
Less complicated, less dense the network, less reactions, and less sort of products that are also being created, right? So yeah.
Okay. Thank you.
Thank you. Yeah.
Okay. Next question, please.
I guess I gave a really good talk. No one has any questions.
Yeah. I think another reason that now, I think it's like two extremes, because people probably would have too many questions.
That's true.
The relative
I was just joking.
Yeah.
I'm pretty sure
because,
that.
Yeah, because data science is still a little bit less unknown field for geologists. So people sort of get lost at where they should begin with.
That's fair.
So yeah. Okay. I could jump in for a second question instead. Are this network analysis computationally intensive? Do you need workstations or supercomputers, or laptop is fine?
A little bit of both. It depends, right? Again, the answer is always going to be it depends, but some of them are very computationally intensive. The fossil networks that we created, some of them are particularly computationally intensive because of the sheer amount of data. I mean, minerals, there's 5,700 known mineral species, and I showed you a network with all 5,700 minerals. That did not require like a cluster or a server of any kind. I just made it on a really good laptop, but I made it on my laptop, right, on a regular workstation. But some of the fossil networks that I made, like the papers that I sent out, had 90,000 nodes. There's like a lot more data there. Those did require to be run on a computationally intensive cluster. Our Studio Server Edition, we didn't have to do too much more to that, but that was a pretty powerful system that we ran it on. So yes. So it depends on the size of the network. Yeah.
So what software did you write this on? Did you use Python or you use C++?
So most of it is in R. Most of the static networks that you see are in R. Some networks are more sort of interactive and we want more features in them. We want them as almost like a web app. Those are all written in JavaScript. So we either use D3.js or Viz.js or something. Most of the other stuff is in R. These networks that are on the screen right now are the only networks in my slide deck that are in Python using NetworkX. But that's just because, Mike Wong, the person who's leading this project, is familiar with that. So he's been using that for the initial networks.
Okay, thank you. Because my interpretation is that, for geologists are slow in picking up data science. Me and some of my students and collaborators were working on Python and also try to build more modules that's more accessible to average users, so that geologists, I think it's still possible for geologists to learn Python because it's relatively easy to get with. But I think that's it, because he asked people to learn
I mean,
3, 4, 5.
there's quite a lot of options. Yeah. So I think, so there's two things I'd like to mention there, right? So the first is that there are like packages and things out there that don't need any coding experience that you can use. There's like Gephi and stuff, which is purely interface based. Like you click some buttons and you can create networks. So if you really don't want to code, or if you're uncomfortable, you can use those. Though I do recommend, if you're interested, to learn at least Python or R to do some of this, because it really gives you a lot of flexibility. Personally, I like R better, especially for the network analysis. But you can go either ways. You want some amount of flexibility to do like some math along with your networks. And the interface only ones don't let you do a lot of network metrics and other sort of connected to some mathematical models and stuff like that. I see a message as well on chat. I can read it out if that's fine with you. So it says, hello, I'm starting to apply ML to some geological studies, but I have basic knowledge on ML. Can you give me some advice on how to begin? Perfect. Yeah. So what I'll do is there's quite a lot of resources out there. Depends on how you want to start out. If you want to start generally learning ML, you can learn about different algorithms. There are Coursera courses out there. There's also just a very introductive thing, but we had a webinar series on data science for geosciences, which is a 3-part series given by 2 of my friends, 2 of my colleagues, Hao Zheng, Fang Huang, and myself. So we go through all the basic steps for data science there that you want to look at. But if you want to start in R, I recommend looking at the book. It's called A Pirate's Guide to R, I think it is called. So just Google that book, or I'll find a link and I'll send it so that it can be shared. That's a pretty nice introduction to R.
So Anirudh, could you type the book name in the chat?
Give me a second. I'm Googling it. There's like a free version there. So if you just wait 1 minute, or if someone else has a question, you can ask it. In the meantime, I'm gonna look for the link and just paste it here. So if you want to start coding in R, I recommend this one, because I like this book, the way it's written, and it's pretty informative. It's very hands-on, so it really gets you in the coding side along with the machine learning side. So learn the machine learning concepts and then code learning this book from this book. Yeah. Did you get the link? Just check it out if it works.
Yes.
Perfect. Yeah.
Very good. Okay, next question, please.
So also no worries while we're waiting for the next question. No worries if you don't have a question now, or if you can't think of one now. You can, I guess I put up my contact on the first slide, but I also put my website here. Just my email and stuff is there. Feel free to contact me.
Yeah. I also list your website information
awesome.
in the webinar schedule. So when people
excellent.
Because we record your talk, so it's great. I really appreciate that. So another good thing is that actually our webinar list for participants in different time zones, some of them do watch their links, or people going back to look for previous talks that where speakers agreed to share their videos, and then there's a link, and then next to that there is a link for their website of the speaker. So so it's like you are not giving one talk, but it's like you are giving the talk for 100 times for whoever access to this Google Sheet. So it's pretty good.
Hopefully the talk was smooth for people to view it that many times, but I'm happy to do that. And just feel free to contact me if you have any questions, or if you have some data that you want to work with me on. I'm happy to talk. Yeah.
Okay, I think that's so much about it for this webinar. Thank you very much, Anirudh, and it's great having you here. And thanks everyone for your participation. So our next webinar will be Wednesday, 9 p.m. Beijing time next week. So I will send information by email. Okay, great. See you next week. And thank you again. And
Thank you. Have a nice
okay,
day, everyone.
have a good evening. Bye-bye.
Bye.